This problem deals with a fascinating device called a cyclotron. It is one of many forms of particle accelerator, and the properties that we derive in this problem are exactly those necessary to understand how this device works. So for this problem, I'm actually going to do two things. First, solve what's asked, and then have a brief discussion on what a cyclotron is and how it works. Part A. Before entering the cyclotron, the particles are accelerated by a potential difference v. Find the speed v at which the particles enter the cyclotron. This part of the problem is exceptionally vague, and I'm going to need to add a drawing in order that we can understand. Let us imagine that we had a capacitor plate, and that a second capacitor plate contained a hole. In this case, if we were to charge these two capacitor plates, let's assume that the one on the left would be charged positive, and the one on the right would be charged negative, we would have an electric field that runs from left to right. As a result of this, any positive particle that started on the left would be forced towards the capacitor plate on the right, and because we have left a small hole, some positive particles will be ejected from the hole and will leave in an energetic state. We'll solve this part of the problem by using energy principles, and as always, the technique by which we apply energy principles is to identify the appropriate moments. We're going to identify moment 1 as when these particles are located at the first of the two plates, and moment 2 when they exit the hole. Moment 1 and moment 2 will be connected by the principle of conservation of energy, and this means that the total energy at moment 1 is going to be equal to the total energy at moment 2. We currently know of 5 forms of energy, and we'll ask at each of these moments whether that form of energy exists. At moment 1, we do not have kinetic energy, since we will release these particles from rest. We do not have gravitational potential energy, because this is negligible in the face of electric potential energy. We do not have a spring. We do not have rotational kinetic energy. However, at moment 1, we do have electric potential energy. And the most general form in which we can write electric potential energy is some amount of charge placed at a location with a particular voltage. At moment 2, as these same particles exit the capacitor plate, we do have translational kinetic energy. We do not have rotational, nor gravity, nor spring, nor at this point do we have any electric potential energy left over. Please notice that in this expression I have tried to use rather different handwriting for the v that represents velocity as opposed to the v that represents potential, because we're going to have both of these in this expression necessarily. Solving for the velocity, we get the answer to part A, that the velocity is the square root of twice the charge times the potential divided by the mass. Part B, find the radius of the circular path followed by the particles, assuming that the magnitude of the magnetic field is B. To solve this problem, we're going to take a simple above view picture of what's going on, and particles at a constant velocity in a magnetic field will move in a circular path, and we're going to label the radius of this circular path as r. We recognize that circular motion is intrinsically a force problem, and so that's how we're going to solve it. Let's identify this location here, and then begin the force problem as we begin all force problems by drawing a free body diagram. This dot will represent the particle that is currently inside the cyclotron. As our next step, we list all forces acting on this particle. One of them is going to be magnetic force, and the strength of the magnetic force is charge times velocity times field. This, in fact, is the only force acting on the particle as it moves through the magnetic field, and so our free body diagram is a single force free body diagram, and it will be obvious what direction we will choose to call positive. We will call this direction to be with the acceleration. And indeed, even though the speed of this particle is constant, it is nonetheless accelerating, and the direction in which it is accelerating is known as centripetal. Analyzing the centripetal direction, we ask ourselves to name any one force in the plus centripetal direction. The answer is clear. That force is QVB. This is the sum of all forces, and as always, the sum of all forces is ma, and indeed there is an acceleration in the centripetal direction. That acceleration is velocity squared over radius. Conveniently, one of these two velocities will cancel with the other, allowing us to solve for the radius of the orbit that the particle takes in the magnetic field to be mv over qb. Because the charge of the particle is known in advance and the magnetic field setting of such a device is up to us, one can see that the radius is said to depend upon the particle's momentum. Finally, to finish out the problem, we return to part C, which asks us to find the period of the orbit of these particles in the cyclotron. In order to find the period, we're going to reference our radius formula and note that the velocity of the particles is explicitly related to their period because each particle travels a distance of one circumference, 2 pi radius, each period. We can put this information into the formula for the radius so that we'll find that the radius is equal to m over qb times 2 pi r over the period. One convenient cancellation later, and we'll be able to solve for the period of motion of particles in the cyclotron. And our result is 2 pi times their mass divided by their charge times the magnetic field. This is the result that we were asked for in part C, but for further discussion, we'll also find the frequency of particles moving in the cyclotron by taking 1 over the previous result. And finally, the omega, 2 pi times the frequency of these particles, is the very simple expression qb over mass. And qb over mass is known in the field of accelerator physics as the so-called cyclotron frequency. Why is this important? Let's move to our picture of the cyclotron and try to gain an understanding of how this device works. As you examine the diagram carefully, you'll notice that there is a dashed line in the form of a spiral, whose beginning is in the center of the cyclotron and whose end is at the edge of the cyclotron, and there are 2 gray disks. Each one is shaped as a capital letter D, and I'm going to highlight them here. These 2 D-shaped disks are further connected to 2 different wires that I'm highlighting in red, and these form the basis for the operation of a cyclotron. A particle at low energy is started orbiting in the center of the cyclotron, and because it is low energy, it will be moving in a very tight circle. However, using our knowledge of the period of motion of particles moving in this circle, we can pull a trick. We can take the voltage on the 2 lines coming in and we can swap this plus to minus. Why would we do that? Well, the answer is if given the appropriate polarity of the voltages on these 2 D-shaped boxes, we will effectively form a capacitor so that the particle will be accelerated each time it passes from one D to another. If we simply created one of the boxes being plus and one of them being minus, the particle would be accelerated at one point in its trajectory, and then, half a circle later, it would be decelerated in going back to the original box. However, if while the particle is in one D shape, we swap the voltages on these 2 Ds, the particle will be accelerated the second time it goes across the gap. Swap again, and it will be accelerated the next time it goes across the gap, because the period of the cyclotron does not depend upon the particle's energy or on its velocity. One frequency can be used for each pass of the particle, increasing its energy over and over again, causing the circle to become wider and wider until finally the particle exits at high energy, having been accelerated in our cyclotron device. And so, in fact, this device, invented by Ernest Lawrence, is the basis of modern accelerator technology and operates simply by understanding 2 principles. One is a capacitor, and the other is a charged particle moving in a circle in a magnetic field.